The asteroid belt is a fascinating region of our solar system, located between the orbits of Mars and Jupiter. This vast expanse of space is home to millions of rocky objects, ranging from tiny pebbles to dwarf planets, collectively known as asteroids. The belt serves as a natural divide between the inner terrestrial planets and the outer gas giants, playing a crucial role in our understanding of the solar system's formation and evolution. The asteroid belt is situated approximately 2.2 to 3.2 astronomical units, AU, from the Sun. To put this into perspective, it lies between 1.2 and 2.2 AU from Earth, with 1 AU being roughly 150 million kilometers, the average distance between Earth and the Sun. This vast region spans about 140 million kilometers in width, creating a torus-shaped area centered on the Sun. Contrary to popular depictions in science fiction, the asteroid belt is not a densely packed field of rocks. In reality, the space between asteroids is enormous, with an average distance of about 965,600 kilometers between objects. This vast separation means that spacecraft traveling through the belt are unlikely to encounter any asteroids unless specifically directed towards them. In fact, numerous uncrewed missions have traversed the asteroid belt without incident, including Pioneer 10 and 11, Voyagers 1 and 2, Ulysses, Galileo, Cassini, New Horizons, and Juno. The asteroid belt's formation dates back to the early days of our solar system, approximately 4.6 billion years ago. As the Sun began to form, the surrounding material started to coalesce into planetesimals, the building blocks of planets. However, in the region between Mars and Jupiter, gravitational perturbations from the newly formed Jupiter disrupted this process. These perturbations imparted excess kinetic energy to the planetesimals, causing them to collide at high velocities and shatter rather than merge into a single planet. The composition of asteroids in the belt varies, reflecting the diverse nature of the primordial solar nebula from which they formed. Asteroids are generally classified into three main types based on their composition: C-type, carbonaceous; S-type, silicaceous; and M-type, metallic. C-type asteroids are the most common, making up about 75% of known asteroids. They are dark, reddish in color, and have a composition similar to carbonaceous chondrite meteorites. S-type asteroids account for about 17% of the population, and are brighter, composed of metallic nickel iron mixed with iron and magnesium silicates. M-type asteroids are less common and consist primarily of nickel iron. The total mass of the asteroid belt is estimated to be approximately 2.39 x 1,000 kg, which is about 3% of the mass of Earth's moon. Despite the vast number of objects in the belt, a significant portion of this mass is concentrated in just a few large bodies. The four largest objects, Ceres, Vesta, Pallas, and Hygiea, contain an estimated 62% of the belt's total mass, with Ceres alone accounting for 39%. Ceres, the largest object in the asteroid belt, holds a unique status as both an asteroid and a dwarf planet. With a diameter of about 940 kilometers, Ceres is significantly larger than the next largest asteroids, Vesta and Pallas, which have diameters just over 500 kilometers. The size distribution of asteroids in the belt follows a power law, with the number of objects increasing dramatically as their size decreases. The asteroid belt is not a uniform distribution of objects. There are regions within the belt where asteroids are more concentrated, as well as areas that are relatively empty. These empty regions, known as Kirkwood gaps, occur at specific distances from the Sun, where an object's orbital period would be a simple fraction of Jupiter's orbital period. Over time, Jupiter's gravitational influence causes objects in these resonant orbits to be swept into different trajectories, creating these gaps. Recent observations have revealed that the main asteroid belt can be further divided into two distinct regions. The inner belt, centered at about 2.8 AU from the Sun, contains primarily silicate-rich asteroids, while the outer belt, centered at 3.2 AU, is dominated by carbon-rich asteroids. This compositional difference provides valuable insights into the temperature gradient that existed in the early solar system during the formation of these objects. The asteroids in the main belt are not static. They continue to evolve through collisions and gravitational interactions. These processes lead to the creation of asteroid families, groups of asteroids that share similar orbital characteristics and compositions, likely resulting from the fragmentation of a larger parent body. Studying these families helps astronomers understand the collisional history of the asteroid belt and the processes that have shaped it over billions of years. While most asteroids remain within the confines of the main belt, some objects can be perturbed into orbits that bring them closer to the inner planets. These near-Earth asteroids, NEAs, are of particular interest to scientists, both for their potential threat to Earth and as accessible targets for future exploration missions. The study of NEAs provides valuable information about the dynamics of the asteroid belt and the mechanisms that can transport material from the outer solar system to the inner regions. The asteroid belt has been the target of several space missions, providing invaluable close-up observations of these ancient objects. Notable missions include NASA's Dawn spacecraft, which orbited both Vesta and Ceres, revealing their complex surfaces and internal structures. These missions have dramatically improved our understanding of asteroid composition, geology, and the processes that have shaped them over time. The study of the asteroid belt and its inhabitants continues to yield fascinating discoveries and insights into the history and evolution of our solar system. As our technology and observational capabilities improve, we can expect to uncover even more secrets hidden within this cosmic debris field, potentially reshaping our understanding of planetary formation and the distribution of resources throughout the solar system.